Good morning. Thank you to CETA and the judging panel for shortlisting us. It was a nice opportunity to discuss some of our innovative uses of digital construction technologies that we've implemented on the Mylan Respiratory project, and lessons learned from that we're taking into future work. So in terms of the innovative approaches that we've taken and we detailed in our submission, similar to a previous presentation, we've looked at BIM-enabled prefabrication, BIM-assisted on-site construction. We've also implemented uses of geospatial engineering design for construction. We've looked at some open data transfer solutions. A little faster. So Mylan are one of the world's leading specialty and generic pharmaceutical companies who manufacture over 1,400 different medicines. After 3 decades in Ireland, the MDRP project represented an expansion of the existing facility. Mercury Engineering were contracted to complete the M&E scope for the project, which represented a value of €15 million and had a compressed project duration of 6 months. The scope included R&D facilities, clean production areas, technical spaces, plant rooms, and ancillary services and spaces such as offices and canteens. A total of 260 people were employed on the project by Mercury at peak, and the construction method made use of building information modelling and off-site fabrication methods. Over 20 kilometres of pipework, 11 kilometres of ductwork, and 19 kilometres of cable train containment were detailed in over 4,000 isometrics, delivered by our project team, and allowed for the construction and connection of approximately 140 tonnes of installed equipment, including 13 air handling units and 14 boilers. 4 boilers, not 14. So our project team consisted of 4 experienced construction professionals under the direction of a project lead. The project team all had extensive construction experience and came to the project off the back of a long-running Mercury BIM retrofit project. From different backgrounds, including plumbing, architecture, civil engineering, the project team's diverse skill set combined well on this job to deliver the better information management necessary to drive the coordination, prefabrication, and installation processes. So given the increased complexities of new build facilities, the ability of mechanical and electrical trade contractors to fabricate and install piping, ductwork, and electrical containment on site in an efficient and timely manner has led to an increase in the need for prefabrication. Prefabrication on its own for these complex elements, without appropriate coordination, detailing, and procurement, can lead to significant amounts of rework on site, which will defeat the intended purpose of the prefabrication and impose unnecessary time and financial costs to the project. The use of the digital construction technologies applied in this case will go some way to assuage these difficulties. On the MDRP project, Mercury Engineering's prefabrication facility in Newbridge was utilised to take input from the co-located BIM hub and produce the necessary spill pieces for completion of the mechanical element of the project. Operating to best-in-class quality and safety standards, the prefabrication facility comprises a Class 10 clean room, including welding area for high-purity pipework, along with low-purity facilities for carbon steel, PVC, stainless steel, and modular construction. From our experiences on previous projects, the coordination of works based purely on a federated model can create difficulty due to misalignment issues from construction. In order to alleviate these difficulties, a series of iterative 3D scans were programmed at key schedule intersections to capture constructed elements. These iterative scans were used as a background conditions model by the modelers and gave confidence in coordination of newly detailed elements. Along with the ability to verify against as-built conditions, the 3D laser scans also permitted accurate point verification and connection detailing. Following field data capture and processing, the information was presented to modelers in a number of different formats. However, the predominant method used made use of an add-in application to the authoring software, which allowed for direct integration of the point cloud database into the modelling environment. This method allowed modelers to directly model through the point cloud and avoid any potential conflict, eliminating the need to clash detect and then remodel, therefore reducing the time taken to produce content or clash-free content. The generation of the 3D model inherent in the BIM process provided us with a powerful tool for assisting the construction project on site, or construction process on site. With traditional methods of issuing general arrangement drawings fast becoming obsolete, the use of a 3D model was used on the project to improve site coordination and enhance productivity. The transfer of the data using the EDA data management platform allowed engineering and constructability reviews to be carried out on site by our foremen and engineering staff, with comments sent back to the BIM hub via the same platform. BIM boxes were also developed which placed a PC on site and allowed site staff to interrogate the model as required to determine appropriate information or necessary information for the construction process. The transfer of data to the client was specified in the BIM execution plan as needing a open standard format. The generation of these required file types were carried out through the construction content added to a federated model and then exported to the required format using an iConstruct for Autodesk add-in. So prior to any project, an evaluation takes place of appropriate softwares. Right. Need to leave it alone. Prior to any project being carried out, an evaluation matrix is developed for the softwares as to what exactly will be required on any given project. In the case of the Mylan project, the matrix and software that was chosen for the project was CADWorks Plant Professional for the development of isometrics for mechanical elements, and Autodesk Fabrication and MEP, Revit MEP for production of prefabricated element drawings and for layout and containment drawings. The interoperability, as I've already mentioned, was handled by the addition of all modelled elements into the Navisworks format and then exported by iConstruct to IFC. So given the large number of stakeholders, both internal and external, an effective means of collaboration was required on the project. The strategy developed aimed to generate the maximum benefit of collaborative arrangements and therefore increase efficiency and effectiveness. Data was shared between the main contractor, the subcontractors through the use of the CDE owned by the main contractor M&W Link. Internal data management was managed through the use of the EDA platform, along with weekly stakeholder meetings, which were used to aid the coordination process. Also, from a Mercury point of view, our BIM hub is also co-located with our fab shop, which enables direct communication between people developing and constructing the spools and also the modelers. So any questions or queries can be easily asked and answered. The need for best practice guidelines to enable meaningful collaboration was a must on the project, and given the diverse nature of the contractors involved, this was handled through the use of appropriate BS and PAS standards, along with the AEC BIM protocol guides to allow for implementation of standard recommendations. In terms of education and training on the project, the training was handled directly in-house through developed modules by our training team. Due to the fact that a lot of foremen and construction workers on the job hadn't previously worked on a BIM project before, a BIM for Foreman course was developed, which was delivered to the BIM foreman. This gave visibility to what a BIM project entailed in the form of a number of questions. How does it work? What does it mean to you? And what is BIM? In conjunction, a Navisworks site training manual was also developed, which gave site staff the basic tools required to interrogate the model as necessary. Also, our BIM modelling staff are upskilled in the use of survey applications, which allowed the direct integration of our point cloud database into the authoring software. The BIM execution plan identified a series of risks to the successful outcome of the project. The silo mentality traditionally associated with construction projects was mitigated through the implementation of collaboration protocols to achieve better outcomes. Safety and design was a major concern for the project. System locations to allow for appropriate and safe operation of the plant were designed effectively using BIM authoring softwares. Access routes were monitored during construction and updated as required in the model. And also the workshop environment inherent in prefabrication eliminates some, if not all, of the site safety risks inherent in a traditional stick-build environment. Cost and time impacts were assuaged with the use of appropriate quality assurance and quality control techniques, including our engineering reviews and our constructability. Accurate as-bills were developed and delivered to the modelling staff to allow for appropriate modelling around existing elements. Project life cycle, predictability of project life cycle was used to avoid any unsatisfactory or unsustainable solutions and driven through the use of 3D visualization in design. So our key project outcomes were the development of our trained staff, which would be of benefit moving forward, and the integration of our BIM and prefabrication workflows, which will lead to our overall company goal of right first time. The successful integration of BIM into the site workflows gave visibility to our construction staff and illustrated to the supervisors the effectiveness of using digital construction technologies. The development of enhanced methods for delivering clash-free model content using high-definition scans helped to reduce modelling time by providing a realistic virtual representation of as-built conditions, and also provided a more transparent third-party method of developing red line drawings at the end of the project. Also, the advanced data management and interoperability capabilities allowed for import and export of information between authoring and visualization softwares. Workflows that were developed specifically for the Mylan project have migrated to subsequent projects and have become part of our standard operating procedures. Our lessons learned from the project: the early integration and alignment of our 3D coordination against construction milestones was evident due to the late award of the project and not having an MEP BIM model from which to design our own content, which meant that construction and modelling happened in parallel. Deviation from construction needed to be captured immediately so as to avoid any abortive 3D detailing works. At the outset of the project, we didn't have full access to the 3D library content which was required to complete the project, and as such, considerable time and effort had to be placed into the creation of this library, as many vendors did not supply specific model elements. This is modelled content that will stand us in good stead on subsequent projects, and also make us aware of the fact that moving forward we will need to ensure that the elements that we need to model are available to us, and time to create our own if needed should be included in any scheduling of works. Training of site staff in simple navigation skills in Navisworks and the upskilling of foremen to understand what the BIM process means and what it can do for them was fundamental in the successful delivery of the project. Communication with the site team and having them responsible for field installation by involving each contractor in BIM coordination and process meetings by allotting time in daily meetings to discuss BIM issues is something that has become standard and will be used on all subsequent projects.